Alright, so welcome back to the second part of the second week. In this part, we are going to actually define formally what a matroid structure is. As I said, it's a combinatorial object that really interestingly captures the sort of structure that we need for the greedy algorithm that we saw last time to actually work. So let's dive into the definition first, and then we will look at a few examples, and next time we will come back and revisit our greedy approach and actually see that it works. So recall that we are working with a universe and a family over the universe. So that's the pair of objects of interest right now. The universe consists of elements that we denoted E1 through En, and the family consists of subsets of the universe which we denoted S1 through Sm. So recall that each Si here is a subset of U, right? What makes such a pair of objects a matroid? Well, we need this pair to satisfy three properties, and I'm going to list them out here. So the first property that we require the matroid to satisfy is what is called non-emptiness, which simply means that the empty set belongs to the family F. This may look like a silly thing to demand, but it turns out that this is the property that keeps our matroids from being completely trivial. So we want to exclude the empty family from being a matroid, and that's why we explicitly require non-emptiness by requiring the empty set to belong to the family so that the family is not empty. Okay, so I hope that made sense. The second property that we are looking for is what is called heredity. And this simply means that if X belongs to F and Y is a subset of X, then Y also belongs to F. So basically, if a set belongs to the family, then all of its subsets are also in the family. That's heredity. The third property, and arguably the most crucial one from our point of view, is what's called the exchange property. And the exchange property is the following. If we have two sets X and Y in the family F, and X is a bigger set than Y, note that I'm not asking for X to be a superset of Y necessarily. I just need for the size of X to be bigger than the size of Y. If this is the case, then what I desire is that there is some element X in X minus Y. Notice that X minus Y is non-empty because we insisted that the size of X is bigger than the size of Y. So there's definitely something in X minus Y, it's not empty. But among everything that sits in X minus Y, there must be something which I can actually add to Y, which is the smaller set, such that this enhanced set Y union X also belongs to the family F. Okay, so that might have sounded like quite a bit that's going on. So let me just recap the exchange property with a diagram. So what we are saying is, if we have a set X which is bigger than a set Y, and it's possible for Y to be completely disjoint from X, it's possible for Y to be completely contained in X, or anything in between. Okay, so we have no constraints on how X and Y interact in terms of containment. All we need is X is a bigger set than Y. And if this is the case, then what we want to say is that I can find some element here in X minus Y such that when I talk about the set Y union X, this also belongs to the family F. Okay, so that's the exchange property. Now, if you're up for a challenge, what you could do is pause the video here and go back to when we were trying to prove that the greedy algorithm works for the generic optimization problem that we set up last time. And you can try to see if this exchange property actually helps you in the step that we got stuck at. Okay, of course, that's something that we will work out properly in the next video. But if you feel like anticipating it or, just thinking about it by yourself, this would be a good time to give it a shot. But you're also welcome to just continue tuning in to this video, where the next thing that we are going to do is look at some examples that will hopefully help give us some practice with the definition and get us comfortable with it. Okay. Just very quickly as a sanity check, if you recall the example where greedy did not work, we had the universe being the elements W, X, Y, Z, and our family was something like W, X, Y, Y, Z, and Z. Notice that this is not a matroid. For various reasons, it in fact violates all the three properties. The empty set is not explicitly included in F. That is one problem. We have XY, but we don't have either X or Y. So we also violate heredity. Of course, we have already violated heredity by not having the empty set, because recall that the empty set is a subset of any set. So that's already a violation, but we have lots of violations of heredity. But also we have a violation of the exchange property, because you have the set XY and you have the singleton set W, and this set is bigger, the set XY is bigger than the singleton set W in size, but neither WY nor WX is an element of the family. So the exchange axiom is also violated. So this is not a matroid for multiple reasons, right? So that's a non-example. But now let's talk about something that would qualify as a valid example of a matroid. So the simplest example of a matroid is the so-called uniform matroid. So what is the uniform matroid? Well, the universe is simply 1 to n. The natural numbers 1 to n. And the uniform matroid of order k, if you like, is simply the family that consists of all subsets of the universe which have size at most k. So fix some k between 1 and n, say. So that would be the uniform matroid of order k. So just to make this example a little bit concrete, let's say that n is 10 and k is 2, right? So then the universe would be the set 1 to 10, and the family would be the empty set. It would be all the singletons, and it would also be all the two size sets. So I'm not listing out everything explicitly, because it's going to be 10 choose 2 sets plus 10 sets, and that's a lot to put on one slide. But you can use your imagination to populate the entire family, right? Let's quickly validate that this family satisfies the matroid properties. In particular, non-emptiness is guaranteed for pretty much any value of k. Now the next property is heredity. Remember, heredity says that if x is in the family and y is a subset of x, then y should also belong to the family. That was our second property. Now notice that if x is an f, because of the definition that we have here, we know that the size of x must be at most k. And now because y is a subset of x, of course if y is the same as x, there's nothing to prove, but if y is a strict subset, then that means that it cannot have more elements than x does. So in particular, the size of y is going to be at most the size of x, or if it's different from x, it's going to be strictly less actually. And therefore y is also going to be at most k, and therefore y does belong to the family, right? So heredity is also satisfied. Now what about the exchange property? Well, suppose you have a set x and you have a smaller set y, right? Then notice that because the size of y this time is strictly smaller than the size of x, once again we are in a situation where we know that x must be at most k because x belongs to the family by assumption, and because y is a set whose size is strictly less than x, we know that the size of y must be strictly less than k, which means that if we add another element to y, then the size of that set is going to be at most k, because even if the size of y was something like k minus 1, even then when we add one element, we are still not going to cross the threshold of k, right? So we can pick any element that is in x minus y, and we know that there's at least one element in x minus y because the size of x is bigger than the size of y. We can pick any element that we like here and add it to y, and we would still be fine. Y union x would be at most k and therefore would belong to the family f, right? So in that sense we are done here, because we've shown that the exchange property holds, heredity also works out, and non-emptiness is also fine, right? So the uniform matroid is indeed a matroid, right? So hopefully this is something that you're convinced of. If not, feel free to pause the video here and make sure that you're comfortable with this example. Now let's talk about another fundamental example of a matroid, which is a linear matroid. And in fact, this is the example that motivates a lot of the definitions and the terminology around matroids. You may have been reminded of the word matrix when you heard of the word matroid, and that's actually an interesting coincidence, because a lot of the matroid terminology is borrowed from linear algebra terminology, and a linear matroid in fact is very intimately related to matrices. So suppose A is a n by n matrix. In fact, doesn't have to really be a square matrix, so let me say that A is an n by m matrix. Now our universe is again going to be just 1 to n, and our family is going to consist of subsets of the universe which are such that the columns corresponding to this subset are linearly independent in A. So A is a matrix which has n rows and m columns. Let's say that that's n rows and m columns. And I think I have a typo here, so the universe is better thought of as being 1 to m. So that's one element corresponding to each column of the matrix A. And if you give me a subset of the column indices, what I'm going to do is focus on those columns alone and ask myself, do these columns form a linearly independent collection of vectors? And if the answer is yes, then that set of indices belongs to my family. If the answer is no, then it doesn't. That is the family that we are looking at. So notice that this is another situation where, given a subset of the universe, you can easily verify if it belongs to the family or not, because in this case you go to that subset of columns in the matrix, and using standard algorithms you can verify if these columns are linearly independent or not. So for example, you can use something like Gaussian elimination or your favorite algorithm to check for linear independence, and so the oracle axis here would be no trouble to actually implement, right? Let's briefly talk about validating the Matroid properties here. So non-emptiness is straightforward because the empty collection of vectors is vacuously linearly independent. There is no dependence to speak of. In terms of heredity also, we are fine, because if a collection of vectors is linearly independent, then any sub-collection of them would also be linearly independent. And finally, we want to talk about the exchange property. So for the exchange property, what we have is one collection of vectors x and another collection of vectors y, where again the promise is that there are more vectors sitting in x compared to y, right? And the question here is, can we always pull in some vector of x minus y into y and still maintain the linear independence of y? Here you can argue that if this is not the case, then you have a contradiction to the very concept of the linear independence of some collection of vectors here. In particular, what this means is that every vector sitting in x minus y can be expressed as some linear combination of the vectors in y itself. Think about what that implies for our assumption about all the vectors in x and y being linearly independent, and you should be able to derive a contradiction. In the interest of time, I'm not going to work through the details of this here, but it is in the assignment, and I would encourage you to actually work out the details using what you know from your linear algebra classes. Okay, so this is the notion of a linear matroid, and for now, hopefully you have enough intuition to justify that it actually satisfies the matroid properties. And once again, I would encourage you to actually flesh out the details of why the exchange property holds. Okay, let's look at one last example of a matroid, and this is the so-called graphic matroid. And this brings us back to the example of spanning trees. So what is a graphic matroid? Well, the universe here is the set of edges of a graph. So suppose you have a graph G with vertex at V and edge at E. Our universe is going to be the set of edges, and the family is going to be a collection of edges such that the subgraph induced by those edges is acyclic. That's the family that forms a graphic matroid. Okay, so let's again try to appreciate why this is a matroid, right? So first of all, non-emptiness is okay, because if you don't have any edges at all, you cannot form cycles, so that's easy. Heredity is also straightforward, because if you have a collection of edges that don't form any cycles, then if you throw away some of those edges, you are not going to create a cycle, right? So if you already have something that is acyclic, then any subgraph of this will also be acyclic, right? So if I just get rid of some of these edges, you might disconnect the subgraph further, but you're certainly not going to create a cycle, because if you did manage to create a cycle, then that cycle would have also been there in the set that you started with, which would contradict the assumption that the set you started with was acyclic. So heredity is okay. Let's move on to showing the exchange property. So once again, recall that we are going to be working with two sets. We have the larger set X and a smaller set Y. And we want to argue that there's something that you can pull in from X. In this case, you're working with collections of edges. So what we want to say is that there is some edge sitting in X minus Y, which you can pull into Y. And, it's still going to be acyclic. Y combined with a new edge would still form an acyclic subgraph of the original graph. Okay, so let's zoom in a little bit to see this a little more clearly. So suppose we have an acyclic subgraph Y. Right. And now we have some other acyclic subgraph X. And what we know about X is that X has more edges than Y does, right? So let me actually in this example write down what the connected components of Y look like. Here is the first one. It has 5 vertices and 4 edges. Here is the second one. It has 6 vertices and 5 edges. And here is the third one, which has once again 6 vertices and 5 edges, right? And the reason I'm enumerating these numbers will become clear in a minute. Let's think about where the edges of X can go, right? So some of the edges of X may be the same as edges of Y, in which case they're not going to be useful for us, because remember our goal here is to pull some edge in X minus Y, add it to this set, and be assured that we still have maintained acyclicity. That's what we want, right? So where are the edges of X minus Y? Let's ask ourselves that. We can have these edges going within a component. We can have these edges being on a completely fresh set of vertices that we have not seen before. We can have these edges sticking out of a component like this, or we can have these edges joining two components like this, right? So notice that we are actually fine with edges of this sort, and this sort. These edges are fine. They can be peacefully added to Y, and we will not get into any trouble with creating cycles. The only kind of edges that are problematic are these ones. So if all edges in X minus Y look like this, then we are in trouble, right? So let's think about why that would happen. Is it possible that every edge in X minus Y is a bad edge for us? Well, if every edge in X minus Y sits inside these components, then let's think about how many edges X can have, right? Because notice that if the edges of X are completely constrained to being inside these components, then X can have at most 4 edges sitting in this component, because remember X is itself acyclic. So if on top of 5 vertices X has 5 edges, that means that X itself is inducing a cycle. So you might remember from your graph theory basics that if any graph on n vertices has at least n edges, then that graph has a cycle. There is no way around that, right? So X can afford to have only 4 edges sitting in this component, only 5 edges sitting in this component, and only 5 edges sitting in this component, right? Which means that X can afford to have a total of at most 14 edges which are fully inside these components. But notice that Y itself has 14 edges, and our assumption was that X has more edges than Y does, right? So that means that at least one of these edges is such that it's not fully inside one component, but is either sticking out or is completely separate or is joining two components. And all of those edges, all of those kinds of edges are fine for us, right? So we will manage to find at least one edge which has the property that it's not creating a cycle. One edge in X minus Y. That is what makes this collection of subsets actually satisfy the exchange property, right? So we have that what we were calling the graphic matroid is in fact a matroid because it satisfies all the 3 matroid axioms. Okay, so these are three fundamental examples of matroids that keep coming up in various contexts: the uniform matroid, the linear matroid, and the graphic matroid. There are many other examples of matroids as well, and you will probably encounter them in other situations. In particular, you'll also see a couple of them in the assignments. But let me also give you one more example of something that is not a matroid, just so that we are careful about jumping to conclusions. Okay, so here is an example of something that looks like it may have enough structure to be a matroid, but in fact it is not. So once again, let's fix the graph. The vertex set is V and the edge set is E. And like before, let's say that the universe consists of edges, and let's say the family is subsets of edges such that X is a matching, and by matching all I mean is that it's a disjoint collection of edges, right? So this would be an example of a matching. This here is not a matching. Okay, so a matching is a collection of edges that don't have any shared endpoints. Okay, so of course if you have an empty set, then there are vacuously no violations, so non-emptiness is fine. Heredity is again fine, because if you have a collection of edges that have no overlaps, any subset of them will also have no overlaps. But now let's think about the exchange property. Feel free to pause the video here and try to play around with this example and see if you can either prove or disprove the exchange property. Okay, so I hope you had a chance to think about that. Let's look at this example here. Here are two edges. Let me call them AB and XY. And this is definitely a valid matching. And here is another edge that connects X and B. And as a singleton edge, that's also a valid matching, because as a singleton edge, again, you vacuously satisfy the matching property. So this set XB here has size 1, and the set AB and XY has size 2. Sorry, has size exactly 2. And of course, this is now the bigger set. So we should be able to pull in something from the bigger set, add it to the smaller set, and still maintain that we have a matching. But notice that that's not possible, because if you try to add either AB or XY to the edge XB, you get something that's not a matching. So you're kind of stuck. The exchange property is actually not true in this case. So this is an example of something that comes close but is actually not a matroid. There is something called a matching matroid in the literature, so please don't get confused. That's a slightly different matroid. It's defined in a slightly different way, but the definition is out of scope for our discussions here. It won't be really relevant, so don't worry about it. It's just that if you encounter a matching matroid later in your life, just remember to look at the definition carefully. This is not what they're talking about. Okay, so now that we've seen the definitions, some examples, and some non-examples of matroids, we are now ready to get back to a greedy algorithm and show that it actually works. And that's going to be the next part. I'll see you then.